Ever get that feeling like you're just drowning in information? Like trying to sip from a fire hose?
Oh, absolutely. It's like every way you turn, there's another wave of data crashing over you.
Exactly. And how do we figure out what's actually important in all of that noise? Well, today, we're diving into a concept that can help us do just that.
It's all about finding the essence, the core building blocks of information.
I like that. So what's the secret weapon we're talking about?
Linear independence. It's a pretty fundamental idea in linear algebra.
Linear algebra. Okay, I can already see some listeners tuning out, but trust me, this is way more exciting than it might sound at first.
Definitely. It's really about understanding relationships. Like imagine you're building something, a tower out of blocks, maybe.
Okay, I'm picturing it. Lots of blocks, different shapes and sizes, all stacked up.
Now, some of those blocks are crucial to the tower's stability. You take one away and the whole thing could topple over.
Makes sense. Those are the essential pieces, right?
Exactly. Those are our linearly independent vectors. Each one brings something unique to the structure, a direction or quality you can't get by just combining the other blocks.
So they can't be replicated. They're the essential ingredients.
Precisely. Now, think about the opposite scenario. Some blocks you could probably create by stacking or arranging others in a specific way.
So they're not really adding anything new to the structure, just taking up space.
Exactly. They're redundant. We call those linearly dependent vectors.
So linear independence is all about finding the blocks you absolutely need, the ones that contribute something unique.
You got it. And this is a big deal in tons of real-world situations. Like imagine you're analyzing a ton of data.
Oh, yeah. Trying to make sense of all those spreadsheets and variables.
Well, linear independence can help you figure out which variables are truly important and which ones are just echoes of others. You can streamline your analysis, focus on what really matters.
It's like decluttering your data, finding the signal in the noise. I like it. But how do we actually figure out if something is linearly independent? Is there like a test?
Absolutely. One way is to use a system of equations. Basically, you set up equations based on your vectors, and you see if the only solution is the trivial one.
Trivial one.
Meaning all the coefficients in the solution have to be zero. It's like saying you can't create a zero result without using any of the vectors themselves.
So if you can create a zero result using some combination of those vectors.
Then they're dependent. At least one of them can be expressed as a combination of the others, making it redundant.
Okay, that makes sense. What about other methods for testing linear independence? You mentioned something about matrices earlier, right?
Yeah, there's another way, especially useful for matrices. It involves something called the determinant.
Determinant. That sounds a bit intimidating.
It's not too bad, really. Think of it as a special number associated with a square matrix. If that number, the determinant, is non-zero, then boom, the vectors making up that matrix are linearly independent.
So it's like a quick check. Non-zero determinant independence.
You got it. But what exactly is a determinant and how do you calculate it? Well, that's where things can get a little more technical.
I was afraid you might say that, but maybe we can break it down a bit.
Sure. Essentially, the determinant tells you about a matrix's scaling factor, how it stretches or squishes space. The actual calculation involves some patterns and operations on the matrix's entries. But the main takeaway is this. A non-zero determinant means those vectors are doing something unique, changing space in a way that none of the others can replicate on their own.
So even if the calculation itself is a bit much, the idea is pretty clear. A non-zero determinant means those vectors are bringing their own unique flavor, their own independent contribution.
Right. It's a powerful concept. And speaking of power, there's another big idea that's tightly linked to linear independence, the rank of a matrix.
Okay, I'm definitely sensing a theme here. Rank, independence, it's all connected somehow.
It absolutely is. But before we get into matrix rank, I think it's worth taking a moment to appreciate just how far we've come already.
Yeah, good point. We've gone from building blocks to data analysis, even touched on systems of equations. And it all comes back to this idea of figuring out what's truly essential, what can't be built from something else.
Exactly. It's a fundamental idea that pops up all over the place in fields you might not expect, signal processing, machine learning. You name it.
It's like we're starting to see the matrix.
Yeah.
Or maybe the framework behind the matrix.
That's a great way to put it. And as we move on to matrix rank, we'll see how this framework becomes even more powerful, how it helps us uncover the true dimensionality of information.
Dimensionality. Okay, now I'm really intrigued. But I guess we'll have to save that for next time.
Sounds like a plan.
All right, so let's pick up where we left off. Matrix rank. What is it And how does it tie into all this linear independence stuff?
Well, think of the rank of a matrix as like a measure of its true size, but not in the usual sense of how many rows and columns it has.
Okay, so not just counting boxes in a grid.
Right. It's more about how much independent information is packed into that matrix. It tells you the maximum number of linearly independent rows or columns you can find in there.
So a higher rank means more independent information, more of those essential building blocks we talked about earlier.
You got it. And here's the cool part. The process of finding the rank is like refining a raw material. You start with this matrix. Maybe it's a bit messy, some redundancy in there.
Kind of like our block tower with a few extra unnecessary pieces.
Exactly. And you go through a process called row reduction. It's a way to simplify the matrix, kind of like chiseling away the excess stone to reveal the sculpture underneath.
So we're figuring out which rows or vectors are truly independent, the ones that give us unique information.
Right. And as you reduce the matrix, you're essentially revealing its true rank, the number of non-zero rows you end up with. That's your rank.
So it's like we're finding the most compact, essential form of that matrix, stripping away the unnecessary parts.
And that rank, that compact form, it tells us a lot about the system we're studying. For instance, if we're dealing with a system of equations and the rank is less than the number of variables we have.
Uh-oh. That sounds like trouble.
It can be. It means that system is either going to have an infinite number of solutions or no solutions at all. It's like having a recipe with too many free choices. You could end up with a million different dishes or none that actually work.
So matrix rank gives us clues about the solvability of equations, the relationships between different variables. It's like a secret code embedded in that matrix.
It really is. And this whole connection between linear independence, matrix rank, the way systems behave, that's what makes linear algebra so incredibly useful in so many areas.
Okay, I'm getting that this isn't just theoretical mumbo-jumbo. There are real-world applications here.
Oh, absolutely. We talked about signal processing earlier. Remember how I mentioned isolating a specific sound from a noisy recording?
Yeah, like filtering out the background noise to hear someone's voice more clearly.
Well, that's a perfect example of linear independence in action. You can think of that audio signal as a combination of different frequencies, different vectors, and if the frequencies making up the voice are linearly independent from the frequencies of the background noise,
we can separate them. Just like removing the redundant blocks from our tower, we can get rid of the noise and keep the important signal.
you got it. And this idea applies to all sorts of signal processing tasks. Cleaning up audio, improving sound quality, even isolating specific instruments in a musical piece. It's all about understanding which components are truly independent and which ones are just adding clutter.
That's incredible. So you're telling me that by understanding whether vectors are independent, we can literally filter out noise and data or even isolate specific sounds. That's way more practical than I initially imagined.
It is, and that same principle is at work in data analysis too. Imagine you're a researcher trying to understand what makes a marketing campaign successful.
Lots of factors to consider there. Ad spending, target audience, social media engagement.
Exactly. And you collect data on all these variables, but are they all truly independent? Or are some of them just mirroring others, not really giving you new information?
So it's like we need to find the key ingredients in the recipe, the variables that have a unique and independent impact on the campaign's success.
You got it. That's where linear independence comes in. It helps us pinpoint those essential variables, the ones that truly make a difference. We can streamline our analysis, build better models, really get to the heart of what's driving the results.
This is reminding me of those minimalist recipes that are all about using just a few key ingredients to create something delicious.
I love that analogy, and in a way, that's what linear independence allows us to do. Find the minimalist recipe for understanding a system. It's about focusing on the essential building blocks, the independent pieces that really matter.
Okay, I'm really starting to see how powerful this concept is. It's not just abstract vectors and matrices. It's about finding the true drivers in any complex system, whether it's sounds, data, or even social phenomena.
And it goes even deeper than that. As we move into more advanced applications like machine learning, this idea of linear independence becomes absolutely crucial.
Machine learning. Okay, now we're getting into some seriously cutting-edge stuff.
Yeah.
I'm all ears.
Let's dive in. Imagine you're training a machine learning model to recognize images of cats.
Cats. Machine learning. This should be good. But how does linear independence fit into all of this?
So think about how a machine learning model sees an image. It's not like us looking at a picture and instantly recognizing a cat.
Right. It's all about data, right? Ones and zeros.
Yeah, essentially. The model breaks down the image into tons of tiny pieces, pixels, each represented by a number. And those pixels, we can think of them as variables, vectors in a really, really big space.
Okay, I'm trying to wrap my head around this. So
Uh-huh.
each cat picture is like a point in some massive multidimensional space defined by all those pixels.
Exactly. But here's the catch. Not all those pixels are equally important for recognizing a cat.
Of course, some pixels probably just show the background, right? Not super helpful for telling if it's a cat or a dog.
Exactly. Some pixels might capture really subtle features like the shape of the ears or the pattern of the whiskers. Those are the ones that really scream cat.
So we need to find those essential pixels, the ones that really carry the information, the catness, so to speak. And that's where linear independence comes in.
You got it. In machine learning, we call this process dimensionality reduction or feature selection. It's about figuring out which variables are truly important and which ones we can toss out without losing crucial information.
So it's like decluttering, but for data. We're simplifying the picture without losing the essence of what makes it a cat.
Perfect analogy. And one common way to do this is with the technique called principal component analysis, or PCA.
PCA. Gotta love a good acronym.
Right, so PCA essentially finds new axes, new directions in our data space that capture the most variation, the most spread outness of the data points. And guess what? These new axes, these principal components, they're often chosen to be linearly independent.
Of course they are.
Yeah.
All comes back to independence. So instead of working with thousands of individual pixels, we can represent the cat image using a smaller set of these principal components, which capture the most important features.
Exactly. We're compressing the information without losing the essence of what we're trying to represent. And this simplification, this dimensionality reduction, has a lot of benefits.
Like what?
Well, it makes our models simpler, faster to train. And sometimes it can even make them more accurate because we're focusing on the features that actually matter. And it all goes back to linear independence, making sure those principal components are each bringing something unique to the table.
Wow. We started with building blocks, then we talked about sound waves, now we're simplifying cat pictures for machine learning. It's amazing how far this concept of linear independence reaches.
It's a powerful idea. And trust me, this is just the tip of the iceberg. As you explore other fields, statistics, economics, even physics, you'll keep bumping into these concepts. Linear independence, dependence, rank, they're fundamental to how we make sense of the world around us.
You've definitely given me a whole new perspective on things. It's like I've gained a superpower, the ability to see the essential building blocks behind complex systems.
And that's the beauty of linear algebra. It gives you this framework for understanding information, for seeing patterns and connections that might have been hidden before.
Well, I'm definitely hooked. Thanks for taking us on this journey. It's been incredibly eye-opening.
My pleasure. Always happy to spread the linear algebra love.
And to our listeners, we hope you've enjoyed this exploration of linear independence and all its amazing applications. It's a concept that pops up everywhere, so keep your eyes peeled. Who knows, you might start seeing the world in a whole new way. Thank you for listening to Podcast Learn and Fun. We hope you enjoyed the journey of learning. If you like our videos, please subscribe, click the like button, comment, and share. See you next time.